Channel IIT Olympiads and AP Physics with Ambarish, and I've been doing a series of videos to build up towards solving the JEE 2016 problem involving double disk rolling on a floor. And it turns out the problem has been handled in a very haphazard manner in most of the places without giving appropriate required theory for 3D rotation. So I have done 2 videos so far. The first video in the series was the video regarding description of principal axis, and then there was one more video in which I explained the previous video where I explained the relationship between the revolution omega, the spinning omega, and the omega of the rigid body. And today we are now moving towards angular momentum, how to calculate the angular momentum, and there's a popular misconception which I'm going to clear in today's video. The students sometimes think that angular momentum has to be always parallel to the angular velocity vector. This is not necessarily the case unless you're talking about angular momentum about an axis which by definition is parallel to omega vector. But if you're talking about angular momentum about a point, we'll see that it may not turn out to be along the omega vector. So let's formally get into the theory. So here's the problem statement. Consider a rigid body rotating with an angular velocity omega vector. Find its angular momentum about part A, an arbitrary point located on the rigid body. So let's say O is some point on the rigid body, and I want to find out angular momentum of the rigid body about a point which is located on the rigid body itself. So this is one, okay. Angular momentum about an arbitrary point located on the rigid body itself, okay. And second is about an arbitrary point located in space somewhere outside the rigid body. Let's say there's some point in space and I want to find out the angular momentum about that point, okay. And what is known as the masses and coordinates of each particle are known, and the velocity of center of mass is also known. So now before I begin the analysis, I want to emphasize that when you are saying angular momentum about a point on the rigid body, obviously you are not assuming a rotating frame attached to that point, because otherwise if you look at the rigid body from a rotating frame located on the rigid body itself, then the whole rigid body appears to be stationary, right? So whenever, and angular momentum will be obviously 0. It's a very boring frame if rigid body appears to be at rest. So generally when we say we want angular momentum about a point located on the rigid body, we are considering a point which is not rotating with the rigid body. I mean, it's always present on the rigid body, but it's not rigidly, like its XYZ axis are not rigidly rotating with the rigid body. It's translating with the points on the rigid body. Alright, so now let's do this problem. So 2 parts of the problem. One is about a point on the rigid body itself, we want the angular momentum, and the other is we want angular momentum about a point in space. So how do we proceed with this? Let's see. We'll go with the basic definition and we'll just keep on deriving and expanding upon the basic definition itself, okay. So we'll do it from the scratch. Let's see how to find the angular momentum, okay. So now let's say there is some particle, ith particle having mass mi, and let's say its momentum is pi, and let's say its position vector with respect to O is ri. So how do we define the angular momentum? You know that angular momentum is nothing but ri cross pi. So position vector cross the momentum vector, okay. So that's what I've written, the definition, sigma ri cross pi. So you need to add the angular momentum of all the particles, therefore there's a sigma, okay. And what can I write for the velocity of ith particle? With respect to O, you know that the velocity of any particle is nothing but omega cross r, okay. So that's what I've written. So this will be, okay, ri, it comes as it is from here, and then ri cross momentum mi times vi. So that is omega cross ri. That's what I've written. So this is basic definition and summation over all the particles. All right. So now what I can do, you see here there is an ri and there's an mi. Mi is a scalar, you can take it anywhere within this expression, and then ri cross omega cross ri becomes the vector triple product, okay. So I'm going to expand this part with the help of vector triple product using the back cap formula you must have studied in your class 12th vectors, okay, in mathematics. So I'm going to use that formula, okay. So ri cross omega cross ri, this part, this and omega cross ri is equal to, you take omega outside and take the dot product of the other two. So omega times ri dot ri and minus second vector, that is ri times omega dot this ri, okay. So this is a standard formula. You can refer to your class 12th mathematics vectors if you want a proof of this formula. I am going to use it directly. It is also called back cap formula, okay. So now Ri dot Ri is obviously Ri square, okay, and Ri times omega dot Ri will be in one more expression. So if I write this, this becomes sigma mi, and using this substitution I get Ri square times omega vector, okay, and minus Ri times omega dot Ri, okay. So now this is the angular momentum, and in principle I can always do this summation over all the particles and I can get the angular momentum. Now let me expand this. Now we are going to get a very expanded kind of expression, because I can write omega as what? Omega will have three components, okay. Omega vector, let's say omega x I cap plus omega y j cap and plus omega z k cap. So I can write omega like that, okay. And what about Ri? So Ri vector is nothing but x times I cap plus yi times j cap plus zi times k cap. That's the position vector of ith particle, okay. Now you just put in omega over here and just put in Ri over here. So in principle you will get something out of it, right? And if you expand, you will get a very huge mathematically complicated expression. I encourage you to do it by your own hands, but I am telling you that it's going to be a little boring exercise, because it's cumbersome, and you'll see the huge expression that you get upon expanding this. So ready for the complicated expression? Okay, so let me present to you. This is what you are going to get if you expand it on in all its glory. So what I suggest is, you can see this is going to be a cyclic expression. So just try to work out the coefficient of I cap instead of working the coefficient of I, j, k simultaneously. Just look at what you will get for the coefficient of I cap, and by symmetry you can write for j cap and k cap. So what do you get for angular momentum? This huge expression. And don't get frightened by this expression, because it's going to get simplified. Why? Because I encourage you to see a video on principal axis that I had done earlier. So if you see the first expression, this is nothing but moment of inertia about x axis, right? Sigma mi yi square plus zi square times omega x. So omega x can be taken outside the sigma, and this is nothing but moment of inertia about x axis times omega x. So this is ix omega x, okay. And what about this? This is, you know, that sigma mi xi yi is the product of inertia, okay. So I'll give the link in the description box if you want to learn about product of inertia. You can watch that video. I'll give the link in the description box, okay. So this is I xy and times omega y, and this is I xz times omega z. So this whole expression, this is the coefficient of I cap, okay. So ix omega x minus ixy omega y and minus ixz omega z, and by symmetry you will get for j cap also. This is iy omega y minus iyz omega z and iyx omega x, and similarly for the z component of angular momentum, okay. So I'm going to write it in the simplified notation in terms of moments of inertia and products of inertia. So what do you get? You get this. So x component of angular momentum is ix omega x minus ixy omega y and minus ixz omega z, okay. Similarly, ly we get an expression like this, and for lz we get an expression like this, okay. Now try to recall from the video on products of inertia that if we choose x, y and z to be principal axes, so in case we choose them to be principal axes, then ixy, iyz, izx, all these things go to 0, and then we get a simplified expression, okay. So if x, y, z are chosen to be principal axis, please watch the video on principal axis in the link in the description box, and it's not very difficult, it's a very easy concept. So if they are principal axis, then products of inertia will vanish, and you will be simply left with L will be simply x component ix omega x, y component iy omega y, and z component iz omega z. So this is the angular momentum about the point O, provided x, y and z are chosen to be principal axis, okay. So whereas what is the omega vector? So omega vector is going to be omega x I cap plus omega y j cap plus omega z k cap, and now you can see that L about point O and omega are not parallel unless either ix, iy and iz are all equal. Then you can take I factor common, and inside you will get omega x, omega y and omega z, okay. In that case angular momentum will become parallel to omega vector. Or what can be the other possibility? Suppose omega y and omega z are 0. In that case this is simply ix omega x I cap, and this is omega x I cap. So that means what? Either you choose either omega is along one of the principal axis, okay. Let's say it's only along x axis, or only along y axis, or only along z axis. In that case L about O will be parallel to the omega vector, but otherwise in general it's not going to be parallel to the omega vector, okay. So we can say that L about O is parallel to omega vector if and only if omega vector is along the principal axis through point O. Okay. So I hope this theory is clear, and now we are going to apply this theory to a particular example to illustrate it further, and so that you get a command over the use of concept. Okay. Now okay. Sorry, so a little bit more, there was second part to the problem, that was we want to find the angular momentum of the arbitrary point in space. So this was angular momentum about the point on the rigid body itself. Okay, so let me also complete the entire theory about the space also, and then we'll look at the example. Okay, so angular momentum about the point, arbitrary point in space is what? So let's say O is now some arbitrary point in space, and C is, let us say, the center of mass of the rigid body, and let's say RC vector is the position vector of the center of mass with respect to arbitrary point in the space, which is O. Okay, so now what is the angular momentum about point O? So we can say that L about O is nothing but Ri cross Pi, where Ri is the position vector of this ith mass with respect to O, and Pi is the linear momentum of point ith mass. Okay, so L about O is Ri cross Pi. Now if you see, Ri vector is nothing but vector sum of Rc plus Ric. Okay, so Ri vector is this vector. Okay, just look at my laser pointer. So Ri vector is from O to this Mi, and this is nothing but Rc plus Ric. Okay, Rc is the vector of center of mass with respect to this, and Ric is the position of center of, position of ith mass with respect to center of mass. So by vector sum, this is Ri. Okay. And similarly, what I can say for the velocity of ith particle, it is nothing but velocity of center of mass plus velocity of this point as seen from center of mass. So that's what I have written. So Ri cross Pi is sigma Mi Rc plus Ric cross Vc plus Vic. I hope you got this expression. So I have broken it in terms of center of mass and relative to center of mass. Okay. Now if you expand this, what you will get? You will get 4 terms. Okay. So what will be the 4 terms? You know that Rc cross Vc, Rc cross Vic, Ric cross Vc, and Ric cross Vic. Okay. That's what we are going to get. So that's what I have written, 4 terms in 4 different colors, and it turns out that 2 terms will come out to be 0. Let's see. So first term is sigma Mi Rc cross Vc. Second term is sigma Mi Ric cross Vic. Now third term Ric cross Vc, and the fourth term Rc cross Vic. So these are the 4 terms you get on expanding this. Okay. Now what you can write, I have written it in another manner. So this first expression is very simple. You can take Rc cross Vc common outside the sigma, and then sigma Mi becomes nothing but total mass of the object. So this becomes simply capital M times Rc cross Vc, where capital M is the total mass of the object. Okay. And what about this term? This is nothing but angular momentum about the center of mass itself. Okay, so this I have written directly. This is angular momentum about center of mass. Now for the third term, what I have done, I have divided it by the total mass and multiplied it by the total mass. So you can always write this expression as m times 1 upon m times this. So I have deliberately written it like this. Why? Because 1 upon m times sigma Mi Ric is nothing but, by definition, coordinate of center of mass as seen from itself. Okay, because sigma Mi Ric upon m is the coordinate of center of mass as seen from center of mass itself. So this obviously is 0, right? This must be 0. So this third term goes to 0. And similarly, what about the last term? So in this, you know that Rc can be taken outside the cross. Rc cross Vic is, Rc is a constant term. Okay, so it can be taken outside the sigma, and it will become Rc cross sigma Mi Vic. And this is what? So sigma Mi Vic is nothing but momentum of the rigid body as seen from the center of mass frame. Okay, and because Mi Vi is what? That's the velocity of the ith particle, right? Momentum of the ith particle. Okay, Mi Vi. But momentum of ith particle as seen from center of mass summation over the entire rigid body is always 0, because center of mass frame is also the 0 momentum frame. Okay, so this term goes to 0, this term goes to 0, and the whole thing simplifies to simply L about O is nothing but m times Rc cross Vc plus Lc. So this can be thought of as this is the angular momentum about center of mass, and you can say this is angular momentum of center of mass, although that's not a very good use of language, but just for memorization you can think of it like the river boat problem, where you say that velocity of boat is velocity of river plus velocity of boat as seen from river. So something like that, just for memorization sake. That's not a very good use of language of physics, although, but you can memorize it like that. So angular momentum about center of mass plus angular momentum of center of mass, capital M times Rc cross Vc. Okay, so try to keep this in mind. We'll be solving the problem now. Okay, so now let's look at an illustration. So Example problem: a thin disk of mass capital M and radius r rolls without slipping on a horizontal surface as shown, such that angular velocity of its revolution is capital omega. So this is the same physical situation that I took in the previous video where I explained various angular velocities. The same situation. Okay. Now, but we have to find angular momentum here. In the last video, we had to find the angular velocities. Okay. So it's revolving with capital omega without slipping. Okay. Okay. So then we have to find angular momentum of the disk about its own center in a translating frame. So here is its own center, and we want to find angular momentum about its own center. Okay. Then second part is angular momentum of the disk about its own center in a revolving frame. So we'll see this, what do we mean by revolving frame. And the part C is angular momentum of the disk about point O on the ground. So there are three problems, distinct problems, that we are going to solve. Right now we'll focus on first part, that is angular momentum of disk about its own center in a translating frame. Okay. So now for finding the angular momentum about its own center, what I can do, so here is the center, and I have chosen x-axis and y-axis such that they are principal axis. You can verify for yourself that products of inertia will vanish about this x-axis, y-axis, and obviously z-axis is along x cross y, that is coming outside, and you can see that these are the principal axis of the disk passing through C. Okay. So now what I can do, so you know that angular momentum, now for angular momentum I need the velocity of point, I need to calculate the omega of the disk. So we had done this in the previous video also, and just so that you don't have to look at that video, I'll just do a small calculation again. So let's say now this is the instantaneous axis, OA is the instantaneous axis of the disk. Okay. And point C, the velocity is nothing but this omega into this orange distance. Okay, so that is omega r cos 45 degree, small omega r sin 45 degree, this distance, and this is capital omega r cos 45 degree. So that gives you omega of the rigid body. Why? Because from this is revolving, right? So C is also revolving with same omega, and this distance is nothing but r cos 45. Okay, so speed of C I have written in two different ways. One is this omega times this distance, and other is capital omega times this distance. Okay, so that gives us the velocity of angular velocity of the rigid body is simply capital omega about this axis. Okay, the blue axis. Okay. And the direction you can see from the revolution, if you curl your fingers in the sense of revolution, you will see that this is the instantaneous axis, and this is the direction of the omega vector. Okay, so vectorially you can write omega vector as what? Now you can resolve this along x-axis and y-axis. So this omega vector, you can see that this is our x-axis and this is our y-axis. Okay, so what will be the components? Okay, so I've made a small mistake here. This should be the j cap component will come out to be positive. Why? Because this will have one component like this and one component like this. So here it should be plus j cap. So let me use a pen, just 1 second. So this should be plus, not minus. Okay, excuse me for that mistake. It's not come out very nicely. Let it be. Okay, this is supposed to be a plus sign. Okay, so this omega vector I have resolved, okay, into I cap and j cap components. Okay, so now angular momentum about C is nothing but Ix omega x I cap plus Iy omega y j cap plus Iz omega z k cap. Okay, so that comes out to be, now here also again there will be a plus sign. Okay, there should be a plus sign over here. Okay, now Ix is nothing but half mr square, moment of inertia about x-axis, and moment of inertia about y-axis will be 1 by 4 mr square. So this is what I have written. Okay, so I hope this is clear, the angular momentum about point C, just using this formula in terms of principal axis. Okay, now so this simplifies to this. Okay, and there will be, now since there is a plus minus change, so this should be, instead of plus, this should be a minus sign over here. This is a minus sign. Okay, so 2I cap minus j cap. Okay, so this is a plus minus mistake. Okay, this will carry forward to the next parts also, so please bear with me for that silly mistake. Now part B, angular momentum about its own center as seen from the revolving frame. So what do I mean by revolving frame? So suppose you sit on the axis of revolution. In that frame you will be only able to see the disk spinning about a fixed axis, right? You will not see the disk revolving at all, because you yourself are revolving sitting on this blue line. So this disk only appears to be rotating about a fixed axis, and this is spinning about some fixed axis. Okay, so now what you can do, now again we can apply the same formula, but with due care to the omega vector now. Okay, so from revolving frame we only see the omega spinning. Okay, now how do I find out the omega spinning? So you can see that if I look at velocity of point A, so since A lies on the instantaneous axis, the velocity of point A is 0. So by superposition you can see the velocity of point A, due to spinning alone it will be omega s times coming out of the slide. Okay, and due to capital omega it will be going into the slide, and the distance will be capital omega into OA. So that will be the velocity inverse, and the superposition of these two should be equal to 0. So I can say that capital omega into r root 2. Okay, so this is capital omega, this is r, and this is r. So this is OA is r root 2. So capital omega into r root 2 is the inward contribution due to revolution, and for due to spinning it is omega spin into r, and that is outside. Okay, and this superposition should be 0 because A is the part of instantaneous axis. Okay, that gives you omega of spinning equal to capital omega root 2. So this analysis I had also done in the previous video. Okay, so now omega spinning, if you write vectorially, you curl your finger in the sense of spinning, so it comes out to be in this direction. Okay, that is the omega of spin. Okay, and now you can simply write again using the same formula, principal axis formula, L about this point, this is supposed to be L about point C, so instead of P read it as C. So this is nothing but Ix omega x plus Iy omega y plus Iz omega z, I cap, j cap and k cap components. Okay, so this comes out to be what? So now this is simply I about x axis is simply half mr square. Okay, and there is no other component except the omega spin, which is along the x axis only. So there's no omega y and there's no omega z. So this itself is the angular momentum about x axis. So this is half mr square minus omega root 2 I cap and plus 0 plus 0. This is minus omega root 2 that has come over here. Okay, and if you write it finally, the final expression is minus 1 by root 2 mr square omega I cap. So this is the final correct expression for angular momentum from the revolving frame. In the revolving frame the disk appears to only spin about a fixed axis. So the simple case of fixed axis rotation. Okay, so this is what you get. Okay, and here of course this is parallel to x axis. Okay, here the angular momentum and omega vector are parallel, omega spin. Okay, why? Because omega is along the principal axis itself. Okay, now part C was angular momentum about the point O on the ground. So here this is the point on the ground, and I want to find angular momentum of the disk about this point. So that we had seen that it was nothing but superposition of two terms, angular momentum about C plus angular momentum of center of mass about point O. That's how I had written the formula. So L about O is nothing but m times RC cross VC plus L about C, and L about C we have already found in part A. So we will just import it from part A and then just superpose this term m times RC cross VC. So what do we get? And what about VC? So velocity of point C, you can see that due to spinning point C has got no velocity at all, but because of revolution omega, so capital omega into this red distance, that will be the speed of point C, and it will be in the minus k cap direction. Okay, so that's what I've written. This distance is r cos 45. So velocity vector of point C is nothing but, you can see, omega speed is omega r by root 2 and direction is minus k cap, so minus omega r by root 2 k cap. Okay, and what about the position vector of C? Position vector of C, you see that it's along x axis itself. Okay, so this is r I cap, so this is the position vector of C. So RC I know and VC I know. Okay, and then I can just take the cross product and find this term m times RC cross VC. So what do we get? So if you simplify this, you will get L about point C. I'm sure there will be a plus minus mistake here as well, I think. Okay, so this has got a k component. Okay, just one second. So okay, sorry, this is, yes, this L about C is imported from there itself, and therefore here instead of plus sign there is a minus sign over here. Okay, we had changed that in the first part. Okay, so L about C is this, and now L about C is this part of the expression, and m times RC cross VC, that we can see. So if you take RC cross VC here, okay, let me use a laser pointer. So RC is RI cap and this is VC. So I cross K, if you take I cross K will be minus J. Okay, So minus minus cancels, it becomes plus. So omega r square by root 2. So m omega r square by root 2 j cap, and then this is the expression again. Here there's a minus sign. Okay, so let me again correct over here. This is a minus sign over here. Okay, so if you take a minus sign over here, now in the final expression also I'll need to make that correction. So what do we get? So if you take 1 upon 4 root 2 common over here, so you get for j cap coefficient, what you will get, I mean I cap coefficient is anyway going to be correct, but j cap coefficient I need to collect properly. Okay, so there is a minus 1 over here, and then if you take 1 by 4 over here, so there will be a 4 over here, right? So just 1 second. So there is a plus 1 and there is a 4, so it should be 5 instead of 3, it will become 5 j cap. Okay, if you collect the coefficients properly, and this I cap coefficient is going to be correct. So if you simplify this, this comes out to be 1 by 4 root 2 mr square omega and minus 2 I cap plus 5 j cap. Okay, so this is our angular momentum about this is about O, this is not about A, this is angular momentum about point O. So this is our final answer to angular momentum about O, and I hope you got the concept of angular momentum about a point, and this video helped you understand the nuances of finding angular momentum about a point and why it is not along omega vector in general. And if you did like this video, please do subscribe to my channel if you are not already subscribed, and please share this video as much as possible with your friends who are preparing for IIT JEE or Olympiads, or if you're a teacher, you can share it with your students who might find this video helpful, and do give it a thumbs up. Thanks a lot for watching this video, and sorry about the silly mistakes, but I hope I was able to correct all of them and you got the concept. It was not a very big hindrance. Thanks a lot once again for watching the video. That's all for this video, and see you in the next one.